Welcome to Calculus. Today we will investigate using the second derivative test to find local maxima or local minima. We'll take a look at one example. Our function here is the cubic polynomial y equals negative x cubed plus 4x squared minus 6. And we want to start off by identifying the concavity. So I'm going to jump to that second task that we've got in our instructions. And so to find concavity, we want to take and set the second derivative equal to 0 and solve. So let's find that second derivative. We got to pass through the first derivative on our way. So first derivative of this function is negative 3x squared plus 8x, which means for us the second derivative is going to be negative 6x plus 8. And then to determine concavity, I need to find where this equals 0 and then look at the signs of the second derivative on either side of that critical point. So I'm going to set this equal to 0 and then solve for x. So I'll subtract 8. I'll get negative 6x equals negative 8. And then divide both sides by negative 6 to get this value, x equals 8 over 6, which I could reduce to 4 over 3, 4/3. So for this function, what I want to do is consider what the sign of the second derivative is. I'll use the prime notation, y double prime, around that value of 4/3. So we could catch it by including 1. We'll put 4/3, we know its value is 0, and then 2. So I just want to take and find what are the signs when I plug in 1 and 2 to the second derivative. So negative 6 times 1 instead of x plus 8, that's 2. So the sign on the left of that point at 4/3 is positive. If I plug in 2, negative 6 times 2 is negative 12 plus 8, that's negative 4. The sign's negative. And so I see for this interval, so we'll say for the function from negative infinity to 4/3, the sign is positive. And so the determination we can make is that that has concave up. And then for the second interval from 4/3 to positive infinity, because the sign of the second derivative is negative in that interval, we would make the conclusion that the function is concave down. And what that tells us is that I've got a change in concavity, which means this point at 4/3 is an inflection point. So I do want to find where is that point of inflection. And the way that I do that is I'm going to take the 4/3 and plug it in now to the original function. So I just need this one point here, 4/3 x, and I'm going to plug it into the original function y. So negative 4/3 cubed plus 4 times 4/3 squared minus 6. So we just need to evaluate that. So that's going to be negative 64 over 27 plus 4 squared is 16 times 4 is 64 over 9 minus 6. So then to solve this, we can really multiply here by 3. And so to combine those, I need to make my denominators for all three 27. So that's going to be negative 64 over 27. I got to multiply the next one by 3 above and below to get denominator 27. So 64 times 3, that looks like it's going to be 192. And then 6 has no denominator, so I'm going to multiply it by 27, and that's going to be 162. So the output here is the fraction negative 34 over 27. And that's our inflection point. So I'm going to put that right here, 4/3, comma, negative 34 over 27 is the point at which the concavity of the function changes from up to down. So we've captured that information about the function. We've got the concavity, we found the inflection point, and now what we want to do is use the second derivative test to find, are there any maxima or minima for the function? So I do want to take, first of all, and find any critical points for the function first, and then I'm going to use the second derivative test to interpret those points as maxima or minima. So let's find those critical points first. Again, we take the first derivative to begin. So I'm going to kind of use this space to the right. We're looking for local extrema. So again, to find critical numbers, I'm going to take the first derivative, which I've already got here. It's negative 3x squared plus 8x. Set that equal to 0 and solve. So for this one, I can factor an x to the left, and it leaves negative 3x plus 8. And I can solve this using those factors. One of the critical numbers is 0 itself. The second one comes when I set negative 3x plus 8 equal to 0 and solve. So I would subtract 8 and then divide by negative 3. And that's going to give me the fraction 8 over 3. So I got my two critical numbers. So what I need to do now is I need to run the second derivative test and find out what's the sign of the second derivative where x equals 0 and where x equals 8/3. So let's just say what the second derivative test says for us, since this is a new test for us. So let's just write it here, second derivative test. And it is to find local extrema. We did use the second derivative to determine some information about concavity and the inflection point, but you can use it also to just decide if I know C is a critical number and I plug it into the function. So if I take the second derivative, plug in C, and if that's less than 0, if it's a negative value, what that tells me is that this point is a maximum. Similarly, if I were to plug in C and the value of the second derivative is greater than 0, I would interpret that as a minimum value of the function. So what we need to do then is, again, take a look at the signs for these two critical numbers I found, so 0 and 8/3. So similar to what we did here on the left, I'm going to set up another table, but now with these 2 points, x, and again, we're looking at the second derivative, so we're looking for the value at 0 and at 8 over 3. So again, I'm going to pick up the second derivative. I'll just highlight it real quickly. That's negative 6x plus 8, and I want to plug in 0 and 8/3. So negative 6 times 0 plus 8 is 8. That's a positive value. And so what that says to me is that this point at x equals 0, that's a minimum. We'll find the y value in a moment. So let's just determine about this 8/3. Negative 6 times 8 over 3 plus 8. So negative 6 divided by 3 is negative 2 times 8 is negative 16 plus 8, that's negative 8. So the sign on the 8/3 is negative, that's less than 0. So that critical number at 8 over 3 represents a maximum. And just to round all this algebraic work out, what we need to find is just what are the y values on the original function. And then we'll add that to our list and we'll be complete. So I'm just going to make a second, really a third table here. X, and again, I got 0 and 8/3. I just want to say what are the y values from the original function y. So negative 0 cubed plus 4 times 0 squared. Those two terms we're going to zero out. Minus 6 is negative 6. So I've got the point 0, negative 6, and I've identified that by second derivative test as a minimum. And if I plug in 8 over 3, negative 8/3 cubed plus 4 times 8 over 3 minus 6. So again, I want to evaluate that. And that's a good one to take to the calculator. So we'll just jump over to Desmos really quickly and plug that one in. So negative 8 divided by 3 to the third power plus 4 times 8 divided by 3, and then minus 6. And that gives us this repeating decimal, 3.481481481. If I wanted it as a fraction, that would be 94 over 27. So we'll go back to finalize, and then we just want to come back to this calculator at the end to say, how does our algebra work look on the graph itself? So again, this output at 8/3 as a fraction was 94 over 27, which had the approximate value of 3.481. And we'll record that. So again, that's 8/3, comma, 94 over 27. And that we had identified as a maximum. So we'll add that to our answer there. And what we need to do is just decide, does this correspond with the graph of the function? So I just want to take a moment to look there. We've really found concavity, inflection point, and the relative extrema. So I just want to plug in the function y equals negative x cubed plus 4x squared minus 6. So there's the graph of the function. To check our inflection point, we were really finding what is the value of the function at 4/3. So if I type in x equals 4/3, we see that that's this point right there that changes from a concave up on the left to a concave down on the right. So what we found algebraically using that the concavity test shows up well here on the graph. Let's check our two extremas. So we found that there was an extreme at 0, -6. We said it was the minimum, and the graph is supporting that claim. The maximum, here it's given in decimals, we found 8 over 3. That is 2 points repeating 6. And then our fraction 94 over 27, about 3.481. And so what we've done with our algebra is supported by what we're seeing here graphically. Thank you for joining for this investigation of using the second derivative test to find local extrema. See you soon.